This is Paul Arranz. Bon dia. Can everybody hear me well in the two rooms? Is it okay like this? Or is it better like this? How is it better? Can I be heard well? Carlos?
The first position was better.
Was better. All right. Thank you. Okay, so we continue like this. Good morning. This morning session, if you have seen the program, we will be talking about solar photovoltaics. Okay, it is the first talk on this module, and because it is the first one, we are going to talk about generic issues. It's an introduction and overview. All right, so let's move on. So briefly, this is the contents of the technology training. Today we talk about introduction, then later on after the break we will discuss about generation, okay? About PV cells, PV modules, the structures, all of that. Then for the rest of the sessions on technology, we will talk about the power conditioning, and then with the components on storage, and also about the configurations we can find across the different PV systems. Off-grid configurations, but also on-grid configurations. Okay. So before we move on, I wanted to have a very quick round across the rooms. Yeah, Dr. Lucas and Edelson, if you can help with these. I would like to hear some opinions. What the people in the course, what do you ladies and gentlemen think? What are the main advantages of PV systems? What do you think are the main advantages or benefits? Please, let me hear your opinion.
A pergunta, colegas, é o que acham do sistema solar fotovoltaico? Quais são as vantagens ou desvantagens? Que experiência que cada um de vós tem? Sim? You have to turn the microphone.
I prefer to speak in Portuguese.
Oh, okay.
Yeah.
Okay.
Nenhum problema.
Primeiro é que é energia limpa, né?
He says it's clean energy.
E é inesgotável, a partir do momento que nós temos o sol.
That energy never ends.
Thank you. Any more opinions?
Mais alguma sugestão? Intervenção?
For instance, solar energy is clean.
Yes.
Yes.
You have to be cheaper because no fuel.
Available all over Mozambique.
Yes.
Did you get it? Yeah, it's available in Mozambique.
Okay, that's good. Any other advantage? Because when we compare solar energy to wind, for instance, wind is also clean and it's also plenty, yeah, endless, probably. What could be the advantage? Any other advantage of photovoltaics if we compare to other renewables?
You are comparing wind and PV because I started now during the meeting. Another advantage, no PV, we have less maintenance compared with wind.
Okay. Okay, thank you. Obrigado. Any other? Okay, that's fine. Thank you very much.
Sorry, can I make any comment?
Yes.
I think another advantage of solar is you can install anywhere. Especially for home systems.
You mean it can be adapted to many applications?
Yes, of course.
Okay, thank you very much. Any other suggestion, any other comment? I think you have done very well. Thank you very much for your participation. All the things you said, I completely agree with you. Yes, of course, solar energy is a renewable energy, is clean. It doesn't create pollution. It is available almost everywhere, except for the night, obviously. We can say it's endless, at least at a human scale. And when we compare it to other renewables, it's very modular, it's very adaptable, yes, it's very flexible, and that creates a lot of possibilities. It can be installed anywhere, okay? That is clearly an advantage. I fully agree with you. And also, because it is mostly electronic and electric system, there are no moving parts most of the time. So the maintenance is less of a worry issue when we compare it to other systems, other renewable technologies that will require more maintenance. This doesn't mean that solar energy does not need maintenance. Solar systems need maintenance, of course, but less complicated maintenance than others, okay? So thank you very much. I agree with you, these are advantages, and we will see all of these issues in detail during this course, together with many other issues, okay? So thank you very much. Now, solar photovoltaic energy. Let's start with some introduction and overview, yeah? Starting from the name, photovoltaics. Okay, this word photovoltaic is the composition of two Greek words, yeah? From photos, which means light, okay? And voltaic, from voltage. If you remember yesterday, we described that one of the most important concepts in electricity is the potential energy, electrical energy, which is conceived with the concept of voltage. So photovoltaic refers to the process of generating electricity from the sunlight, okay? And this happens thanks to an electronic process occurring naturally in certain types of material, okay? Some of these materials are natural. We call these materials the semiconductors, okay? We can see in this diagram here a summary of what happens when the light photons, yeah, the photons are the units of light, hit the semiconductor. There is a series of transformations which creates electric flow in DC, in direct current, okay? I will describe this process a little bit further later on. The primary energy, the primary source of energy, is the sun, el sol. Okay, some of the advantages, yes, but also some of the limitations that the solar photovoltaic systems have. For the pros, for the advantages, somebody said, yes, it's abundant and it's everywhere. I agree with that. Also, it is well distributed. We say in the sector, we say it's a universal resource, okay? It's economically competitive. It's environmentally sustainable. It does not pollute the air or the water. We have to be careful with, of course, with the materials and the recycling, especially with the batteries and some hazardous substances that could be there with the acid in the batteries, etc. But as a whole system, generally, okay, doesn't have polluting elements. It is silent, doesn't make much noise, does not disturb or endanger the ecosystems, and it has low maintenance because of the lack of moving parts, as we said. Very modular, and it can adapt very much to the existing buildings. This is a very important aspect of photovoltaics, okay? In Mozambique, perhaps at the moment you haven't yet started to explore all the possibilities of solar PV integrated into buildings, okay? In the cities, in Maputo, okay, for instance. But there's many possibilities there. We will talk about this during the course, okay? When we look at the limitations, the cons, yeah, of course, solar energy is not continuous during the day. It's intermittent. We don't have generation at night. It depends on the weather and the seasons. If it rains, if it's cloudy, we will have less solar generation, okay? Solar PV panel production, okay, it's quite intensive in energy consumption. And during its manufacturing, of course, it emits some gases, it has some environmental impact. But the environmental impact we get from solar systems, it's largely overcome by their production of energy and the benefits. We will have a session on environmental impact of PV later on in this course, and we will have a close look at all these issues. Another limitation is that there are some solar cells technologies that require very expensive and to some extent quite rare materials, okay? Such as the copper, indium, gallium, selenide, or the cadmium telluride technologies. Finally, another limitation, which could be quite important sometimes, is the space requirement, okay? The PV modules, they require substantial area, surface area, especially when we consider PV parks or PV farms, parques fotovoltaicos, they can require a lot of land, and that can be a limitation. Okay, the resource, the solar resource. This is a map of the solar irradiation on the floor, horizontal irradiation in the world. And we can see that the tropical area of the world, especially Africa, is blessed with a lot of solar energy, okay? It is estimated that the sun on average sends about, you can see, is a very large number, 154 million of gigawatts instantaneously to the world, okay, to the earth, okay? 154 million gigawatt instantaneously. That's the continuous, okay, energy flux from the sun to the earth. So on average, the sun delivers to the earth approximately 154,000 terawatt hour in 1 hour. This is the amount of energy that the sun sends to the earth. That's the theoretical potential of solar energy. That's all the solar energy that we receive in the earth in 1 hour. So just to put these figures in perspective, Here in the Earth, we receive from the sun in just 1 hour more energy than all the energy that we consume in the world in 1 year. I repeat this, the sun sends to the Earth in 1 hour more energy than the one we consume in 1 year in the Earth. So it's a tremendous, it's enormous amount of energy we get from the sun. Now we start narrowing down to the case of Mozambique, which is the focus of our attention in this course. And we have very good maps. We have already very good maps. We don't have to worry about finding information on solar energy. All of this is now available to us. When I started working in solar energy, that is 20 years ago, some of this data was not there. We didn't have solar atlas, solar maps like now. And we used to have to go back to some meteorological models, complicated algorithms from NASA in the US, from optical physics, to try to estimate what would be the solar radiation levels in the part of the world we were trying to work. Again, in the last 10 years, there has been a lot of work by different institutions, also Mozambican institutions, to be able to collect and prepare maps like the ones we are looking at now. This is the maps we took from the Global Solar Atlas, okay? It was prepared by the World Bank and the SMAP, using the database from SolarGIS. There are many other sources, okay? But I like these maps, they are quite good. And this website, the Global Solar Atlas, is very helpful, okay, to assess what is the solar resource in a particular town or area in Mozambique. In here, we can see two maps. The one on the left, it's the global horizontal irradiation. That is the amount of energy that is received on the floor. You can see the scale at the bottom. We have the daily totals and the yearly totals. Let's look at the daily totals. That's the amount of energy from the sun received on the Mozambican floor, soil, on the Mozambican ground, per square meter. And you can see there is solar energy being received in Mozambique, in all the country, yes, but not all the towns, not all the parts receive the same amount of solar energy. This data is on daily average throughout the whole year, okay? For instance, in Maputo, we can see it's more in this green color, which means that Maputo receives an average of 4.8, approximately between 4.8 and 5 kilowatt hour per square meter. Kilowatt hour per square meter of solar radiation per day, okay? The other map, I don't like it so much because that between the map on the left and the map on the right, there are some hypotheses, there are some assumptions being taken. The map on the right says the photovoltaic power potential. So this is an estimation of how much electricity you can generate with a PV system in Mozambique. But this map is not telling us which kind of PV system we're using, okay? Is it grid connected? Is it with batteries? Okay? So there are some assumptions there. So please don't take the numbers of the map on the right, don't use them if you don't really investigate what are the assumptions they considered when they prepared these kind of maps. The one on the left is fine. That is the sun received. That is an input we can always use. The one on the right, it's already a calculated map, okay? I'm saying that because sometimes engineers, when they design PV systems, they go very quickly to tools like this, and they take figures like the ones we find on the right, where we could say, okay, so in Maputo, I go to this map and I can see that I can generate 4.2 kilowatt hour per kilowatt peak. And that is a reference for all the time, kilowatt hour per kilowatt peak. I install 1 kilowatt peak, I generate 4.2 kilowatt hour. Well, that's not always true. That will depend on the kind of PV system, okay? This particular map has considered grid-connected PV systems, but if we want to design a mini-grid, then the production will be much less than that, okay? So just a bit of a warning on the maps. Okay, in the introduction yesterday, we described a little bit about what's going on in terms of solar PV evolution and capacity. Well, we see that Mozambique is little by little progressing, installing more capacity of solar plants, but still Mozambique has a long way to go, okay? We can see, for instance, compared to South Africa or compared to the general trend in Africa, we can see Africa as a continent in the last 5 years has started to install a lot of PV, and Mozambique has also started, but very, very timid, okay? Little by little. So there's a lot of potential to be tapped, to be realized in your country. So we have to make it happen, okay? A very important aspect of photovoltaic technology that we mentioned yesterday, the reduction of the cost, okay? We have seen significant, very important cost reductions, okay, in the solar photovoltaic components. Why is that? Well, first of all, there is a pressure to use, we need to use clean energy. We are in a context of global warming, yes, climate change. We have to take action. Technology has matured. Yeah? The technology now is much, much more efficient than 20 years ago, 10 years ago. We have learned a lot in these years, okay? And the production costs of technology have reduced. There's more competition, there's more volume in the market. You can see in this graph here, the evolution. We are now in 2020, and the production for the years to come, the projection, sorry, for the years to come is also to continue this reduction trend, a tendencia, a reducción de costes, okay? This graph is telling us costs in dollars per kilowatt. And we can see from an overall cost of almost $5,000 per kilowatt 10 years ago, we are now to roughly $1,200 per kilowatt. Be careful, these are big numbers. These are average numbers for all photovoltaic systems, okay? This is just as an overview. Don't take that as a reference to calculate the price of a mini grid or of a solar park, okay? This is just the tendency, cost reduction. Another way of looking at that, yes, is not to look at the cost of the installation, the capital costs of technology in dollars per kilowatt, but also look at what we call the levelized cost of energy, LCOE. This is the levelized cost. I don't know how you translate in Portuguese, but it's costes medios or costes nivelados, okay? That is the cost in dollars per kilowatt hour. That's the average cost of every unit of energy, of electricity that will be generated by the PV system, okay? So when we look at this, average cost has also reduced dramatically in 10 years by a factor of 6, okay? So 1 unit of electricity generated by a photovoltaic system, today it costs times less. 6 veces menos, huh? Of what it used to cost 10 years ago. That's a tremendous reduction, yes? You haven't seen that reduction in any other technology in the last 10 years, okay? Levelized cost, sorry, this is a bit of mathematics, but the levelized cost, we calculate it in this way. It's the sum of the different types of cost we have: investment cost, maintenance cost, fuel cost if necessary, okay? And we annualize this, okay? We take into account the discounted, you know, the discounted in financial analysis, we use annuity. We take into account the discount rate, the tasa de descuento, okay? And then for a number of years, we do this analysis and we divide these costs by the amount of energy that is produced every year, okay? So this is how we obtain the levelized cost of energy. And this is, you will read a lot of, you can read a lot of materials that refer to levelized cost of energy. Okay, this is how it is calculated. And there's many tools that also use this parameter.
One question, please.
Yes.
How we find the discount? What is the way to find it, please?
Thank you. That's a very good question. Thank you very much. This question, who asked this question? Can I have your name or your institution?
Renewable Energy Directory, Tenjoa.
From which institution?
EDM.
From EDM, okay. Thank you very much for your question. It's a very important question. The discount rate, it's not a technological parameter. Huh? It's economics, it's financial. This has to do with a combination of different macroeconomic parameters: the inflation rate, the interest rate, and the level of volatility in our currencies, okay? It's not the same inflation we find in the national currency, mexicais, than the inflation you find in dollars, okay? So normally, to use discount rates, to use the levelized cost, I don't like to use them to obtain absolute figures, absolute numbers, números absolutos. I like to use a levelized cost to compare different options under the same parameters. So the discount rate, you can use 10%, 20%, 15%, okay? So far, you use the same discount rate to compare different options, then you're fine, okay? You're using the same inflation under comparing different scenarios. Because if we start discussing with economists, they will never agree what is the correct discount rate. And it's something that will change, okay? Some economists use, 15%, 12%. You can check in your national bank, yeah, the central bank of Mozambique, what kind of discount rate they recommend to use, okay? And that will also depend from the point of view of your financial analysis. We will have specific session on financial analysis later on in the course, where we will discuss with you options, how to go about the approximation of discount rate, inflation, etc. But these are parameters that are not technological in any case. And we can probably try to get references from some multilateral agencies like the World Bank or the government of Mozambique, rather than try to calculate it ourselves as engineers, because it's not really a technological parameter. Let's.
Well, if I may, just 1 second. Indeed, I think for Monday morning session, we will start looking at some of the financial and economic assessments. And discount rate will be part of that. Although I'm not sure if we really managed to go into depth, But if there's a specific interest in this, then maybe we can add some sheets to discuss this a bit further, because it's a extremely relevant question in financial and economic analysis. Thank you.
Yes, yes, exactly. So later on in the course, we will revisit this aspect of discount rate. But in any case, the point I'm trying to make is that it's not a technological parameter that we can calculate. It is a reference we need to get and compare, and we need to get some consensus across the different actors involved in a project. Okay.
Question. You
Thank you.
You have here fuel. What kind of fuel are you talking to? Are you talking capex or?
No,
Yes.
in the
Expended.
okay, in the OPEX, for instance, when you have a mini grid, you can have a hybrid system. Yes, you can have a genset support, a backup. Okay, and
Thank
then
you.
you will have fuel.
Understood. Thank you.
That's fine. Okay, very quickly, just going through these generical parts. Yeah, the worldwide capacity to manufacture PV modules has tripled in the last 6 years. So again, the market is growing, is booming. Yes, the top manufacturing countries. Basically, we have China at the moment leading, yes, with some other Asian countries, Taiwan, Malaysia, South Korea, Japan, India. So the Asian countries are leading the PV cells and the PV module production, with some testimonial presence of North American and some European countries. But this is mostly an Asian dominated market. Okay, very quickly on environmental issues. Yes, we will, as I mentioned, we will have a dedicated session to that. Just we need to remember the different steps in the transformation of a PV system, from raw materials acquisition, we have processing of materials, we have manufacturing steps, we have the use phase. We have then, once the system will be old, we will probably need to uninstall it, decommissioning. Eventually we can recycle some parts, and then the parts that cannot be recycled, they need to be disposed of. So that would be the life cycle of a PV system. So the environmental impacts need to be analyzed step by step in the life cycle. Okay. Very quickly speaking, okay, the PV modules are the most impacting parts, okay, of the PV system, and it happens because at the manufacturing, at the production stage, a PV module is a very sophisticated component that requires a lot of energy. Okay, also batteries can require can pose a significant impact, but batteries are very much recyclable. Okay, it is more of a problem of logistics to organize the collection of the old batteries. Okay, the key components in a solar system, I guess you are in the rooms here, everybody is familiar with the components of a PV system. We have the PV modules, we call the generation field or the solar arrays. Yesterday we remember about direct current. So the PV cells in the modules, they convert the solar radiation into direct current. The other main component we typically find are the charge controllers. The charge controllers limit the electric current flow from the PV generation to the inverter, to the batteries, okay? And they also take care of the state of charge of the batteries. The next component, main component we find typically in PV systems are the inverters. The inverters are the electronic components that will convert the DC current into AC current. And finally, the last main component in a PV system, which can be there or cannot be there, are the batteries. Some solar systems don't need batteries if they are connected to the grid, for instance. Some other systems, they are not connected to the grid, and therefore, normally, we would need batteries to have electricity at night. Here we have the different functions. Okay, in a topologic description of a PV system, we find the sun through the radiation, sends radiation to the PV cells that transform the radiation into electricity. This electricity in direct current is modulated by the charge controller, which can be, adequate the voltage. That voltage and that electricity is then sent to the batteries. If there are batteries, we are still in direct current, or this electricity can be sent to the inverters, either directly from the charge controllers or through the batteries. Okay, so that's a topological representation of a PV system. A very important concept. And I don't know if after that we can take a break if you want, or we can continue. Very important concept is the general efficiency of a PV system. Okay, we call this parameter the performance ratio. Okay, the performance ratio, PR. This is the measure of the efficiency of a PV plant. And that means the proportion of the energy that is actually produced by the PV system after deducting all the losses that take place in a PV system, and also the self-consumption. Okay, so if you remember, from all the radiation that will fall on a PV panel, all the radiation cannot be converted into electricity. There are losses, okay? There are pérdidas, okay? This is what we measure with the PR, okay? So it's a comparison, is an efficiency ratio between the incident amount of energy compared to the final produced energy. And this is the formula. We have the energy that is delivered by the irradiance, that is the amount of the flux of solar radiation that hits the PV panel under specific conditions. I will describe that later on, which you call the standard test conditions. Then the reference, the maximum amount of electricity, this is calculated by the nominal power of the PV generator, that is in watt peak or kilowatt peak, okay? Multiplied by the irradiation that effectively is being hitting that PV panel, okay? How are these kind of losses? First of all, the temperature effect. We will see later on today that when the PV modules, they get warm, they get hot, they lose a little bit of the performance, okay? If you have hot temperatures, very hot temperatures, then a PV module is less efficient. Then there are losses due to the modules mismatch. Some systems that are not well balanced, especially in solar parks, lots of PV modules, this can be a problem, okay? The cabling, their resistance. Remember yesterday, well, we were remembering about electricity aspects, yeah? The losses in the cabling, the losses in the batteries, in the charge controller, in the inverters, etc., etc., etc. Okay? So all of this, in the end, will mean that when we have off-grid systems, a good reference for the performance ratio is between 60 to 70%. Okay? When we are in grid connected, because we don't have batteries normally, okay? Because we have better engineering typically, we have the grid as a reference for power, the way the inverters can work, okay? For grid connected systems, then the performance ratio is higher. We can assume 70% or even 85% if it's not too hot, okay? but it is an efficiency. Remember, we are engineers in the room. There's no machine, there is no process that will have an efficiency of 100%. There will always be losses, okay? So these are, I think, to me, this is a very, very important parameter for you engineers in the room and technical people when you have to evaluate projects, okay? Performance ratio. I don't know, shall we continue, Dr. Lucas, a little bit more, or do you want to have a break now? Because it's more than 10 a.m. Dr. Lucas, shall we continue?
Yeah, I think you can make it 50 minutes, so you still have some 10 minutes to go.
Okay, thank you. So I will continue until you tell me to stop, okay?
Okay.
All right. So one of the advantages of photovoltaics, we said in the beginning, they can be adapted. Yes, you can install them anywhere. We can see in this graph, yeah, for all types of applications. We can have here in the vertical axis the population density, very dense areas, urban areas, to more rural areas or remote areas, okay? And then on the horizontal axis, we can see the energy intensity, basic consumption, medium, large, intensive, and we have all sorts of solar solutions for that, from very simple systems, solar lanterns, solar home systems, then to more, complex systems like mini grids, solar pumping systems, or grid connected systems, okay? So basically, with PV systems, we can do everything, like somebody said in the room, yeah? Somebody said in the beginning, you can do everything with PV systems, okay? The technology is not the limitation. We might have limitations of space and obviously limitations of money, okay? But the technology is not the limitation in general terms, obviously. Okay. Main configurations. On Friday, I will explain to you configurations in more detail, yeah? But very quickly speaking, we have the off-grid family of systems and the grid-connected family of systems. Today in the world, between 90–95% of all the solar systems installed are connected to the grid, okay? And between 5 to 10% are off-grid systems. That is the global, in the whole world, okay? In Mozambique, it's different mix. So essentially, grid-connected systems or off-grid systems. But then also we have hybrid, okay? We have mixed systems, hybrid systems from the point of view of the generation, meaning that these systems, they can rely on one or more different backup systems, okay? Apart from solar energy, they have other sources of energy, could be renewable or non-renewable. But also we have hybrid systems in terms of the distribution, meaning PV systems that have the capacity to work both at the same, both off-grid and on-grid, so they can connect and disconnect to the grid, okay? Some examples, we can see here mini grids, okay? This is a system that I worked in Ghana, mini grid with the World Bank 5 years ago, 4 years ago, okay? When I was working in this company called Trama Tecnoambiental. It's a very, very nice company. You can find a lot of references from their work, yeah, also in East Africa and Mozambique. So with Trama Tecnoambiental and other partners, we built 5 mini grids, and this one was the only mini grid that was hybrid with photovoltaics and wind. You can see the wind turbines here. Other examples, this is a graphic from the company from Switzerland, Studer Innotech, and we can see that when they design their products, this company, they manufacture inverters and charge controllers, okay? they take into account the possibilities of different generation technologies, solar panels, genset, diesel, hydro project, you see, and also some other solar panels, but connected to the grid, okay? The talk we are having tomorrow we are going to have a very interesting session with 3 gentlemen from the industry. One of them, engineer Pablo Muñoz, works here in Studer. So tomorrow, please be interested in knowing the experience of Studer. They will share with us how they approach the design of mini grids and how they design the inverters and the charge controllers to suit and to optimize the energy management in a mini grid. Okay. Tomorrow will be very nice session, you will see. Okay, some other configurations. This is very much of interest for everybody, but especially for EDM. Yeah, the EDM colleagues in the room. The possibility to interconnect the mini grids. Okay, interconnection of mini grids between themselves, but also connection with the grid. Okay, we will have a session specifically on the interconnection of mini grids. Okay, this will be next week on Wednesday. Okay, and we will have again 2 specialist engineers that are working in this field. Okay, we have been doing a project in Nigeria, the government of Nigeria and GIZ. We have been working in the interconnection of solar PV mini grids. And one of the situations we see in the interconnection of mini grids is that we need to account for an evolution of the grids. Okay, today we don't have this possibility, but then little by little we can grow the grid connection between mini grids and eventually the grid itself. So we need inverter technology that can evolve and can adapt to the different operation conditions of the grids. Okay, this is a vision from the Rocky Mountain Institute, what they call the undergrid communities. Okay, this is a concept they have developed to describe what happens in those communities that are placed underneath the high voltage or the medium voltage transmission lines and that are not connected. Okay, this is the undergrid communities. Okay. Next week, we will describe this configuration very much in detail. Finally, another configuration that I'm sure very soon you will start considering in Mozambique, what we call the smart grids, okay? Smart grids, probably for cities, where you have common grids to share electricity, but also you can share heat, you can share cold and even data, yeah? So that's a super grid, okay? Where different uses in a city, like school, like or industry, households, electric vehicle charging stations, whatever, hospitals, etc. Every single consumption point we can think of could be connected, right? Connected by a same grid or network, okay? This is very much the future, okay, for Mozambique, but very soon you can start developing this kind of innovation. Why not? In Mozambique, why not? You can consider possibilities like this pilot project sometime in the near future, okay? This is happening in Europe a lot at the moment, in the US, and in Ghana, South Africa, they're starting to consider these concepts, okay? So very soon in Mozambique, we can also start talking about smart grids. Why not, okay? Okay, very quickly, off-grid applications. Probably I can skip this one because on Friday we will discuss this in detail. So let's not spend too much time on this, off-grid applications. examples of off-grid applications for vehicles, for telecommunication stations, yes, remote lighting systems, pumping systems, etc. Okay, many examples. On Friday we can look at this in detail. For grid-connected applications, again, we have families, okay? Not every grid-connected application is the same. We have the small size, we also call them residential systems, typically from 1 to 10 kilowatt peak for private houses, public buildings, or parking lots, etc. We have medium-sized PV systems, what we call sometimes the rooftops, okay? For commercial applications or in industry applications in a building, okay? These systems are typically from 10 to 500 kilowatt peak, okay? At the moment, we are doing a project with, we are going to start a project with the government of Ghana to help the government in Ghana to map all the country in this range, medium-sized PV systems, to map what the possibilities to introduce PV systems are in all the public buildings in Ghana. This is a project I'm now starting with my team for the next 3 months, 4 months, okay? We'll be doing this mapping for the government of Ghana. And finally, we have a very important category, which are the large-size PV systems, the distributed PV parks or the centralized systems, the PV farms, like the examples that yesterday were mentioned, plant in Mokumba. We're trying to organize a talk within this course about the Mokumba plant, 40 megawatts. So it's a grid-connected PV system and a large case. We will also have a session on the 9th of December, Wednesday, that we will be describing examples of solar parks, okay, we have worked on. Okay, again, I'm not going to spend much time here. What are the typical configurations in grid-connected systems? I think we can have a look at this on Friday. And also tomorrow, we will be discussing about mini-grid configurations with our friends, colleagues from the industry, okay?
Oh,
Yes?
so after the following, the next slide, when you finish that one, we can have a break.
Yes, you see, I was just getting into the break. You see the perfect timing we have?